All right. Okay, just now, before we stop for a break, we arrive at this equation. All right, CV dimension plus CS dimension equal to your force dimension or moment time cross momentum. All right, now basically what is the differences between the previous chapter? As you can see, we have a cross relationship in our equation. Okay, so these are the area of differences compared to the previous one. Just take note. All right. Next, you're going to look at, recall the vector relationship that we learned previously. The V equal to W plus U for moment or momentum chapter. So again, what is V? V is absolute velocity. W is a relative velocity. U is a velocity that measure to a fixed coordinate system. Okay. All right. So later you will see what is U. Okay. Now, if you look at the left hand side of the diagram, you're going to explain what is V, W, and U. So if you look at this one, the W2 is what you see from here. This is your reference plane. Okay, because you are looking at Z from Z rotation axis. Okay, so if you stand here at this place, the red color zone here, when you look at the spray of the water from the sprinkler head here, you're going to see what is the speed of the float relative to your position, which is called W. Okay, so W is what you see from your position at the center or at your reference axis. In here we call it, in textbook we call it fixed coordinate system, right? CS. So the V is absolute velocity, which is the float velocity. Float. The keyword is float. So as you can see here, the float is coming out from the nozzle here. And V is what you measure if you put an instrument here. You try to sense the velocity here, then you get V. However, W is what you see from here. Okay, what you see from here, you'll see W2. What you measure at this point will give you V. Okay, now U, as you can see, now U is opposite direction. Why? Because it's the velocity of the moving nozzle. U is nozzle. Where your nozzle move? This is your nozzle, right? Where is the direction of your nozzle move? Backward, right? Your nozzle move backward, right? So that's why your U is pointing up rather than pointing down. Okay, just recap. What is the differences between these three? First, you look for your, I would recommend you start with, maybe you start with the float. You look at the float, you try to imagine at the opening here, and you carry a sensor here. You try to measure the float velocity, so you get V. Float is coming out from this opening in this direction, so you get this arrow. Second, you look at relative. Relative means you stand at one point. In this case, you stand at the center here. You look at what happened to the acid flow. Okay. You look at the acid flow. Or maybe a more direct one, you just imagine you sit at here. Okay. Because here I take some note here is you view from nozzle, means you sit here And then you look at what happened to the flow. The flow is flowing from W2. Okay, so just imagine, yeah, I think it's better you imagine you sit at the nozzle there lah, rather than at the center. Okay, you just imagine you sit at the nozzle here, and then you look at what happened to the flow. Okay, for W is the relative. So you sit here and then look at what happened to the flow. The flow is spraying out in this direction. You get your W. Then the third one, okay, how you get the U. The U is nozzle. Where the nozzle move? U is nozzle. So again, if you want to, here we refer to a fixed coordinate system. It's either you sit here or you sit here, or maybe it's better you sit at the center. And you look at the nozzle. You look at the nozzle. What happened to this component? Does it move up or move down? So U, in this case, it moved up. Okay, it moved up because it's moving directional, anti-clockwise directional, by referring to your W, omega, RPM, revolution per minute, okay, or radian per second. Okay, and there's a conversion from RPM to radian per second. You know that 360 degree, 360, equal to 2 pi radian. Okay, you have to recall the conversion between degree to radian. All right, clear with VWU. Stop me if not able to differentiate V, W, and U. One is float, one is relative velocity, and another one is the nozzle. Okay, float, relative velocity of your acid flow. Okay, and the one is nozzle. All right. So again, just to remind you, this component can be positive or negative. So because why? Because you are looking at a dot product here. There's a n hat here. So n hat means is a vector component. So how do you know is a positive or negative? Again, if the flow is go into or inlet, go into the control volume. So let's say you draw a control volume. The flow go point this way. The flow go into the control volume. The whole thing, this one, will give you negative. Okay, V dot N give you negative sign. Do the same for outlet. When you have an outlet or referring to outlet location, you get positive sign for this one. Okay, positive or negative depend on whether it's outlet or inlet. When it's inlet, negative. Outlet, positive. You look at one example later on. Okay. All right. Now, I'm going to show you what happened in the axial direction. All right. So looking at this component, yeah. So how do you arrive at m dot? Okay. How do you arrive at m dot? The first thing will give you m dot. How you know it's m dot? Rho A V. Rho AV. Okay. V dot N is velocity. Rho AV give you m dot. So just remember, for moment or momentum equation, the mass flow rate will always positive. Will give you positive. No matter it's rotate or not. This one is just a side note. Whether your sprinkler is stationary or rotate, the mass flow rate still same. you give a positive value. Okay. Next slide is going to show you the direction for this one. R cross V component, and then this one, how do you know whether it's positive, negative? This one you can look at your right hand rules, right? So if the U and V same direction, now for example, in this case, you look at U and V direction, if they are showing same arrow, it give you positive products. In this case, you see the V and U is opposite. Later, you will use negative. That's why you see a negative sign on the right hand side of the equation. Yeah, so these are the sensitive area where you need to take note when you solve for your final exam. Okay, so again, be careful on the positive, negative. You need to be careful on the arrow. And I already explained how you draw the arrow just now. Okay, by looking at the definition of U, V, and W. So then you look at the arrow. If same direction, positive, opposite direction, negative. In this case, this system, this example that you see on the left-hand side corner of your screen is negative because opposite direction. So just to remind you that we have done with the positive, negative sign. The next one, you're going to pull in the torque definition. So for the control volume, the sum of control volume, which is this one, we already completed explaining about this component already. Now we are explaining about this one. When you take force cross R in the control volume on the right hand side in the axial direction, so it will equal to torque. Okay, which is your hand, your thumb. This is your hand, thumb, right hand rules. This is your thumb direction. So this is your forefinger, the cross products. Right? So it will be the same. How we know it's positive, negative? Your torque will be the same of the rotation. In this case, is your omega. Omega. So I'll move a little bit faster now. So by having these two equations just now we talk about minus R plus M. Now we add one more equation which is equal to positive shaft. So as you can see, when you have a positive, means that you will follow the omega direction, or in another meaning is that it will agree with your right hand rules. Means you'll follow your forefinger. Your forefinger is anti-clockwise. The thumb is going up. All right, so this is anti-clockwise direction, and the thumb is pointing up. Then you get positive. All right, so we equal these two together. Okay, we equal these two together because this side just now we define as this one. Okay, and we define the right hand side component equal to T plus this one. So we equal top direction equal to bottom direction. We get shaft T shaft equal to minus RV times M dot. One is negative, one is positive. I just explained the positive and negative sign just now. If you're not clear, listen back to the previous lecture. Listen back to this video again. Go back maybe 5 minutes ago to listen what I explained just now. Okay, there are some notes. So as you can see here, what I mean by this statement or this equation? This equation is based on this diagram. What does it mean? It means the shaft, the top of your shaft, which is opposite of the rotation of the sprinkler arm. So because your sprinkler arm is opposite, is opposite, and the shaft top. Okay, no, this one later lah. Important you understand how you get this one. Then the next one you add in, where usually when it comes to sprinkler or moment of momentum, there will be one section asks you to calculate shaft power. Okay, the shaft power, the turning power of this sprinkler system or turbine system or water jet system. So what is the definition of power? Power equal to W dot, capital W and the dot up there represent power. Shaft means you're referring to the shaft. Equal to T shaft equal to T times omega. Torque. This is your torque. This is your rotational speed. Okay, so when you take your T times W, you get your power. Okay, this is another important equation. Will give you 1 mark if the question asks you to score to find power, shaft power. You write W dot shaft equal to T shaft omega, get 1 mark. Okay, substitute the T plus or plus T definition into T shaft here. You get this one. Okay, I'm going to go a bit slow because something added to the equation now. As you can see here, what happening? Suddenly you have a U2 here. How you get U2? If you compare side by side, you take R2 times omega, you get U2. Okay, R is the arm times omega, you get U component. Okay, so this is a hidden information. Usually in the question, there will be one particular section will ask you calculate U2. The equation for U2 is R times omega. Omega will be given, R2 will be given. So this basically is a bonus mark if you understand what is U2. Okay, now this is bonus mark. Because R2 will usually given, omega will be given. You take omega times R2, you get U2. Another one, after you calculate power, the question will continue to ask you to find per unit mass. You ask you to find work per unit mass. You find work per unit mass given by, you take power divided by m dot. Okay, you take power divided by mass flow rate, m dot. You get work per unit mass. Work per unit mass. I use small w and then with a sharp notation, sharp. So if you divide with m dot, you cancel the m dot, you arrive at minus U2V. Okay, so you get m shaft, w shaft, small w shaft. Okay. What meaning if you get negative? It means this is also important. You need to explain the negative answer. Negative means the work is done by the fluid on the rotor or shaft. The work is done by the fluid. This is the keyword that we are looking for. Okay. If it's positive, then it means another way around. It means rotor or shaft work on the fluid if positive. If you get negative, means the water or the fluid is the one who work on to the structure. Okay, yeah. Again, listen this one many times to understand what mean by negative. All right. Let's look at this example and then we call it a day. Okay. All right. Now this example also available in your handout. So let's look at this system. So if you look at this system, already give you the control volume, and the water is no water. Yeah, this one use water. And the water is spraying from, not spraying, but is input from below, and then it's spray on both ends. Okay, area is given. The arm is given, or the R is given. Unit here is mm. So be careful when you convert. Q here is in ml, so you need to do conversion also. If can, you stay with the unit SI. Okay. Right. Now, what happened if you compare this example to the continuity equation? There's a differences in steps, but it will give you different calculation, because continuity equation in the previous session will ask you about the mass flow and all this. However, when it comes to moment or momentum, it will ask you more about torque. Okay, so when I combine the two concepts, I combine the continuity equation and moment of equation, it will be a very long question. So it can be combined to become one question. Right. So let's look at the question statement. So we have a sprinkler system that fit with the 1000 ml per second steady flow from bottom. And exit area of the two nozzle given 30 mm square. The flow leaving each nozzle is in tangential direction. It is this one. Radius from the axis of rotation is given. The arm R2 is 200 mm. You need to do three things. First, find the resisting torque required to hold the sprinkler head stationary, meaning you find the force at your torque shaft here. Okay, the T shaft. Second, find the resisting torque associated with the sprinkler rotating at a constant speed, 500 revolution per minute. The third one, determine the speed of the sprinkler if no resisting torque is applied. So we are looking at three scenarios here. How would you solve this kind of question? First, you look at a few scenarios. Of course, when you solve this kind of question, copy the diagram and put in your answer there. Okay, copy the diagram and put in your answer so that you understand all the parameter. You don't need to refer here and there because if MCO continue, your exam is going to be online. Okay. All right. So we'll use a fixed non-deforming scenario. So as you can see, the control volume is highlighted in this form. Then we're going to look at axial torque only. That is given in the diagram, which is a T shaft. Okay. Next one, you draw a diagram with the velocity V, which is V is the fluid velocity. Oh, let me erase. V is the fluid that you measure. Just imagine you every time you see V, you carry a sensor to sense the thing, the quantity. So you install a sensor here, you install a sensor here, then you measure. Okay, if you measure at 0.1 here, then you get V1. You put a sensor here, you get V2. Okay, And here, V2 will equal to tangential velocity V0 theta 2, because this is 0.2. Okay, this is 0.1, this is 0.2. Same, huh? So V2 equal to V theta 2. Once you have the diagram by referring to the fluid velocity, V, and recall that we just derived the equation for T shaft. T shaft equal to, as you can see here, T shaft equal to negative R V theta 2 plus m dot. So control volume, fixed, non-deforming. Flow is tangential, means is why tangential? Because if you draw a circle, right, at the center, what mean by tangent of the circle? It means it's only touching on one point of the circle and is always pointing either this way or this way. It means this direction is called tangent or tangential. Okay, that meeting at one point. All right, now this one will give you V theta 2 equal to V2. So I'm not going to repeat the how you find the V2. Okay, refer to tutorial question 12. The same procedure to find V2. Go to the tutorial question 12, already covered in the lecture. So go back and listen to the video, or you can go back to the previous slides. Go to the question 12. Okay, you go and find your V2 equal to 16.7 meter per second. Again, this one you need to refer to the previous one, right? Same steps, but you can find 16.7 meter per second. So m dot equal to rho AV, or AV equal to Q. So this equation is famous for this module. So rho AV equal to Q, give you 1 mark if you write this equation out. So you calculate based on a table for the water at a certain temperature. So you have rho and area. So in this case, your Q is given, right? Rho, your Q is given in 1000 ml per second. You need to change to liter, and then, okay, you need to change liter to meter cube. So 1 meter cube equal to 1000 liter. You use this one, convert. Okay, 1 meter cube equal to 1000 liter. You change this one, you're going to get your m dot in kilogram per second. Okay, rho is given in table. Usually there's a chart behind the exam paper. So rho will be given in a table form at a certain temperature. So Q is given in the question. However, Q is in ml per second. So you need to change this ml to liter. And then when you need to cancel the m cube here. So you need to convert liter to m cube so that you can cancel the parameter and left out kilogram per second in the equation. Okay, your m dot equal to 0.99 kilogram per second. Again, this is sensitive to temperature. Need to refer to table. If this one, you are not giving the correct answer, I will just put a correct question mark there. You will sure get the wrong answer for the remaining one. So I don't need to mark further. Okay, I just put a question mark and I stop there. Okay. So m dot you get already. Then you substitute inside here. V you have R2 half, you get a negative sign, Newton meter. Again, unit is Newton meter. Okay, so if you can't remember what is torque, again, recall back what is torque. Force cross distance. Force is Newton. D is meter. Newton meter. Okay. All right. Now again, I already explained why it's negative just now, and what this negative means. The next one, the second case, B. What happens if your sprinkler head rotate at constant speed, 500 revolution per minute? So the flow in the control volume will be unsteady, but you are seeing a cyclical, means it will in this circle domain. We will assume that the flow is steady. Again, this is a very important concept, but this is in real case. Real case means it will not be stable. But when you do calculation, you assume it's steady. So if you put in all the W, U, V that we mentioned just now, right, the definition of U, V, and W, you'll get this diagram. So as you can see here, your V and U is opposite direction. So you get a negative sign in your calculation. So V equal to W plus U. So as you can see here, your V2 equal to W minus U2. And how you calculate U2? We already mentioned U2 equal to R times omega just now. Okay, omega is given, R2 is given. You managed to find what is U2. All right. Again, U2, you calculate V2, you calculate from tutorial question 12. V2, we already find. Same procedure. Okay. So, and tutorial 2 is W. Okay. In this case, you copy the V2 value from question 2. However, when it comes to this tutorial question, it will become W2 value. Okay. In this case, your W2 will take the value from question number 2, number 12. The W2 value will be 16.7. Okay. So you substitute, you get what is your V2. V2 is 6.2. Just be careful on the conversion of unit. Okay, I'm not going to show you the detailed calculation, but just to check your final answer, you'll get V2 equal to 6.2 meter per second. All right. And then your T shaft just now will be, if you substitute the V2 answer into the T shaft equation, we did this one, minus RV times m dot. For second scenario, your V2 is 6.2. Your T shaft will be negative 1.24. Okay, T shaft will be 1.24. It will be a bit lower compared to case A. Case A give you minus 3.34 when the sprinkler head is stationary. So again, is still approved in a logic way. If your head is not able to move, there will be more twisting moment feel by the shaft here. Okay, because the water is spraying, so something going to turn the head, but the head cannot move. So head cannot move, there's a resisting force, so it's a bit higher. So what happens if you let the head rotate at certain speed? So when you allow the head to turn, the resisting force or the T shaft will be dropped a little bit from 3 to 1.24. Okay, this explain a bit logic on your answer. So when you resist it, the T shaft will be higher. If you let it turn at a certain speed, you need less resisting force. Okay. Then what happens if the C, when there's no resisting torque? So, physics concept, when you do not resist it means the sprinkler head turn freely. So you will meet a scenario where the maximum constant speed of rotation will happen. So you meet your constant rotation will be maximum. So how to find the maximum? So again, use back the three equations just now. T shaft equal to negative RV plus m dot. Use the V equal to W2 plus U2. U2 equal to R omega. Okay. So you replace the theta 2 to V2. So at the end, you will get T shaft equal to minus R2. And you substitute this equation here, you will get W2 minus R omega times m dot. And since there is no resisting torque, right? This is the error when students do try to solve. For if there's no resisting torque, it already tell you already in the statement. It already tell you no resisting torque. It give you some hints. T equals 0. Your torque equals 0. It means this component straight away give you some bonus mark already. T sharp 0, as mentioned in the question. Okay, so straight away on the left hand side of the equation 0, and you solve for the remaining one. You will get your omega, because the third one is to find the speed of the sprinkler, which is the rotational speed. Remember to change the unit when you do calculation, especially that I mentioned just now. What are the unit involved? Is that you need to change RPM to radian per second. Revolution per minute, okay, means you're turning 360 degree over 1 minute. Change 360 to 2 pi radian. 1 minute have 60 seconds, and so on. So do the conversion. All right. Then you manage to find, okay. Yeah. So in this case, just to cross check your answer, omega will equal to 797 RPM. Okay, 979 RPM. If you look at the question statement, so yeah, okay, it will take some time to process, but the step is I show on the screen here. Okay. Okay, why? Because if you look at this, you have the m dot, you have the w, you have the r, you have the r2, you only left out this one. Okay. What happened? The next question is that what happened to the angular momentum? Okay, this one is another hint. Try to think what happened to the angular momentum when there's no resisting torque. So the hints will be the water enter and leave the control volume with 0 angular momentum. Okay. When there's no resisting torque, means it's free flow. There's no friction, there's nothing. So when there's no friction, then it's free to move. Another word is that you're having a 0 angular momentum. Okay, with this I end the recording.